My name is Joe Mahoney. This is the Effective Speaking class at Nichols College. Today I'll be talking about geometric tolerancing, what it is, why we have it, and how it's applied. Geometric tolerancing is the application of geometric symbols to engineering blueprints and the manufactured parts from which they're drawn. The reason we have this engineering procedure is so that all the parts and assemblies will run true to each other, airplanes will take off, cars will stop when the brakes are applied, military weapons will fire when they're needed. Without geometric tolerancing, none of this would be available. Where this came about was the American Society of Manufacturing Engineers and the American National Standards Institute created ANSI 14.5Y, which covered geometric tolerancing, the application, and the fundamentals on how it's supposed to be applied. Older prints may or may not have this. At one time it was deemed not necessary, but now this stuff is much more high speed and precision and accurate. These two groups decided to create this standard. It's also recognized in other different handbooks, like the Machinist Handbook, and the American Society of Manufacturing Engineers also have a full training module on it. To start with geometric tolerancing, they'll have a blueprint, and what they'll do is they'll have what they call a starting point, or a datum. This is datum C. What they'll do is they'll reference other dimensions on the print, like this runout and this angularity, and reference it to datum C. Datum C is only a starting point. That's one of the more important features on the print, so everything else has to run true with it. Now, knowing that, I'm going to give you a quick example here of your car, tire, and axle. You have an axle and a tire. Here's the front view. You can't see the axle because the tire is in the way of it. But what happens is, as the axle turns, the tire turns with it. So without geometric tolerancing, this tire might not turn on the same center of axis as this axle, thereby creating a thump, 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 thump on your tire. And it'll wear out quicker, and the mechanics will wear out quicker. So with the geometric tolerancing, they created a datum, the starting point, made that the axle. The tire has to run true within that axle, total runout to datum A within 6 thousandths. This is called the tolerance block. That tells you everything on here you need to know. You have a datum, you have another feature, and you have what it has to run out true with. Because we have this, what will happen is the geometric tolerancing will control, make sure that this tire, this dotted line represents the tire, isn't sitting crooked to that shaft. It'll sit truly perpendicular to it, 90 degrees. Because they give you an allowable amount over here of 6 thousandths, this could actually be skewed a little bit. But if it's skewed, it still has to fall within that tolerance zone. Also what it'll do is it'll also create the center of the part, so that as this tire goes around, it's going around in a true circle, so that you don't have wear on the axle, wear on whatever's driving the axle will be the transmission, and wear on your tire. It could be unsafe, it could knock down your gas mileage, it would be ineffective, it would also affect your brakes. You go to hit your brakes and your tire is now just chattering and not really giving you a true stopping power. So this is a very basic example of geometric tolerancing in its simplest form. You can picture if you had a large steel mill or an airplane where they put the thruster on, it ignites something else which turns the wheel, which makes everything move. You could have many, many, many of these in one print. They all have equal importance, but if they're drawn on there, then they have to be on there. They have to be adhered to, I'm sorry. So this is very basic. There's many tolerances. Sometimes you can have a stack up in the tolerance block of 4, 5, 6 different tolerances, referencing different angles, different amounts of being out. So, in conclusion, again, this is geometric tolerancing. It's applied to all high-speed stuff, and the purpose of it is to ensure that everything runs in time, You don't have this condition here, you don't have this condition here, and it makes all our moving equipment safer, faster, and more accurate. And this was a very good thing that the American Society of Manufacturers Engineers did by creating this standard, 14.5Y, so that uniformly across the world, in the country, all the parts are made within the same realm of an engineering standard. I hope this explained what this was, and it's a very, very interesting topic to me. It's what I do for a living. So, thank you very much.